All right, we'll go and get started here. So yeah, welcome every guys, the four of you that are here. We are recording, so anything that we do and say will be on there just for the posting. So I appreciate you guys coming out, even though if it is recorded. So I'm Brendan, I'm your TA for the course, and like I was telling Taha here, I am also taking it with you guys because it's the first year course, the first time it's been offered at Mac. So if you have questions, I'll do my best, but if I don't, I'll just pass it on to Dr. Sabri and then get it answered, but I'll try my best. So yeah, I did InchViz undergrad here, and now I'm in CS doing an MEng under Dr. Kret. So I'm sort of CS person, but have a little bit of quantum background. So hopefully answering your questions best possible. Might as well just do a roundup on names. I know Taha, but what about you other three and your names and what's your programming year?
Chris, I'm in my last year of software engineering.
Nice, okay. Chris?
Dionysius, also in my last year of software engineering.
Dionysius?
And Shazwell, also last year of software engineering.
Okay, awesome. Well, yeah, thanks for making the trip out here today, guys. It's going to be a real simple tutorial and real short, so I'm sorry for doing the trip out here for something so short. But first, I don't suppose any of you guys have the textbook, and you can get it whichever way you want to. But we're going to start out with a real simple example from the textbook and then go from there. I'm going to page 113 for anyone following along. So we're going to start out with a really simple example, and I'm going to do everything from the computer. So if anything's hard to see or my head's blocking it, let me know. So this example down right here on page 113. So we're imagining in this case scenario, we got the notation here, but we've got a circuit that's got 3 qubits moving along, C, A, and B. And then it's going to produce something where it produces C, A, and then this like function here where you're adding A, B, and C and then taking modulo 2 of it. So just a basic like base 10 addition, like no bitwise addition or anything, just like we're adding those two and making a simple circuit out of it. I want to get started here by just doing something real simple, real straightforward, and you guys can do it your own on Excel or anything like that. But what I want you to do is just make like a basic simple truth table for the inputs and outputs of what this statement is. And if you have any questions, please interrupt me. But basically just something you can do in Excel or do in a Word, whatever works best. Actually, let me see, maybe I'll put this on the side here and put this on the other side. Get that out of the way. Yeah, but something that'll look like C, A, B, and then we'll call it like, I'll call it C prime, but it's just the C on the other side of the equation, A prime, and then A plus B plus C mod 2. Or I guess if we want to use that mod 2. So something like that, 0, 0, 0, and then obviously 0, 0, 1, and then do the outputs. So yeah, paper works. Also, the other thing works, so. I'm assuming all you guys are super familiar with logic tables and stuff like that. So okay, cool. Might as well, I'll follow along while you guys are doing it, just do it in real time. Everybody all good? If not, no worries if you need a little bit more time. Okay. All right. So yeah, we'll just take this up. So I'm assuming everyone, something looks a little bit like this. I'll zoom in actually a little bit so that actually looks a little bit higher. So pretty straightforward on the first one. The first two rows are obviously, or the first two columns, sorry, are going to be absolutely the same. But then the next one, we're just going to take the sum of those three numbers, and then if it's anything above 2, we'll put it to like, whatever the remainder of the division by 2 is, or something like that. So first one's going to be 1, next one's going to be, or sorry, first one's going to be 0, next one's going to be 1 because the sum is 1, sum is 1. Then here it's 2 divided by 2 is 0, remainder. 1, sum is 2 divided by 2. Oh wait, sorry, that's 0, and then 0, and then 1 because it's 3 divided by 2, remainder 1. So the truth table, if you guys have it, should look something along the lines of that. I'm assuming that's what everyone got. No questions. Everyone's all good with that. Okay, cool. So now the tricky part is how do we want to actually make a circuit that's going to represent something like this and then gives an output of something like this. So the easiest way to think about it, actually, they say it in the actual like definition here. But here we have two actual like things that it's going to define the sum of C, A, and B. So in the actual equation, they put A control XB, or the controlled not, is one of the statements, and the other one is C controlled B. So if you're to put that in just simple language, that's if A is true, or if A is the logical 1, then it's going to make the line B go not. So if A, then not B, essentially, else just normally B. So basically, to make this sum, we're going to do these two things. So I know you guys probably don't have the most familiarness with Composer, but if you want to try it on your own, well, not if, like, let's try it on our own. And sorry, I'm kind of giving away the answer there. But let's try and reproduce this sum circuit on Composer. Does everyone have, I keep calling this Composer, IBM Quantum Composer, does everyone have access to this, sign into that, and everything like that? I can show the actual URL if that is needed. Yeah, quantum-computing@ibm.com. If anyone needs it. Yeah, get onto that real quick. Oh, that is spelled wrong. Let's make sure the recording is still going. Okay, cool, it's still going. Okay, anyone need to sign up for that, or everyone just good to go? Anyone played around with it yet, or followed along in tutorials? Yeah, no, absolutely, no worries at all. It's like, why would you? So as you can see, like, it's a really nice graphical interface that they have. So it's like really fun and easy to play around with. Fun, depending on who you're asking. So as we went over in class, there's just simple graphical interface that you can drag over the different lines. So the biggest thing to look at is at the bottom here, you can see all the different states. So basically we have 3 qubits open, Q0, Q1, and Q2. And then there's a line of classical things at the bottom. We don't necessarily need that right now since we're not measuring anything. So I'm going to remove those. So everything you see in the graphical interface is one-to-one with the actual code syntax on the right-hand side. So it's usually structured left-hand side, this graphical interface, right-hand side is textual syntax, and then at the bottom are your displays. Like you have your probabilities there, and then you have your Q-sphere, kind of like the unit sphere that Dr. Sabri talked about in class yesterday. So I'm going to get rid of these classical lines in the code here, and then it should get rid of those C ones at the bottom there. So this is just a basic, like, really simple setup, just 3 qubits labeled 0 through 2, and we just got a simple line here. So by default, the program will always say the lines are set to a logical 0, or like a 0 qubit. So that's right now, if you look at the bottom, the probabilities, it's going to state that 0, 0, 0, because we've got nothing in there right now. So very simple, like if there's zeros on the lines, we expect it to be 0 100% of the time. If we throw a NOT gate on one of the lines or any of the lines, you'll see 2 things happen. One, it's going to set the bottom probability. That's actually 1, 0, 0. It just doesn't show the other zeros. But it's now this line is a quantum state of 1, or a classical bit of 1, and then that's 1, 0, 0. If we then do the same to the other things, we can add NOT gates, and then it should be 1, 1, 1. Pretty straightforward. You also see that on the right-hand side, the textual syntax will put the actual NOT gate on them. So you could change that around if you wanted to, and just put it to a 1, and then it'll put the NOT gate on the next one, and you'll see it goes from there. The other thing you'll notice is that the way that it reads out at the bottom, it goes 1, 0, 0, So that kind of corresponds to the way the lines are read out. So 0 is 0, the middle one is 0, and the last one is 1. It's kind of sometimes confusing to read, but at least it like lines up 1 to 1. So if you're ever having trouble reading that, just make sure that you're reading it the right way, because I've flipped it in my head a couple times. So yeah, that's generally, there's no way to set the line to like a logical value of 1. So if we need to make it set to a 1, it's like a NOT gate, and we throw that in there. And then as we saw in class, there's the C NOT gate and the Tolfi gate, which is the C controlled NOT gate. But we're going to just start out with a simple C NOT gate. And in this one, we're imagining that, actually let's start with a simpler example where all our lines are 0. This one, if you remember the controlled NOT gate, what's going to happen is it'll reverse or not the third line only if the first line is set to a positive value of true. So in our example, we see that everything's 0 because nothing is set to 1, so it's going to stick with 0. But if we add a NOT gate on the first line here, you're going to see the output is going to switch. Because now that our one line is set to 1, that means that it's going to flip the line number 2. So Q2 will go from 0 to 1. So now our readout at the bottom here will show 1, 1, 0, which is 1 and 2 are set to 1, and 0, since there's nothing on, there should be 0. So pretty straightforward, hopefully. Any questions about that off the top or anything with following along? Okay. Okay, so this is like the easiest and simplest before we install Qiskit. But before we install Qiskit and start to actually like work in the actual program language, this is just a nice simple graphical interface to use that. So it's the basis of where we want to start off. Now, so what we're going to want to do to create this other circuit, and yeah, you guys will follow along for this, is we're going to want to create basically this circuit that they defined here, where the sum is right there, the sum of C, A, and B. So we can choose to define our lines as whichever we want. For now, I'm just going to call 0A, 1B, and 2C, so ABC, just to keep it logical, because I can't figure out if it's reordered or not. And what we're going to want to do is make it so that A control B, or the control line is on A, and it's going to flip B. And then for the next, then another C NOT gate where it's the control line is on C, and it's going to flip B if that's positive. So just if you could try making that circuit just on your own. And the way to flip things around, in case you didn't notice, is you'll put in the gate. And then you have to actually flip it. I don't know if there's a way to flip it in the actual graphical syntax, but you flip it in the textual one, and then it turns it around. So if you need to flip it around, so that's the simplest way to do it. What's up?
So when I drag this C NOT gate,
Yeah.
it just shows up as a NOT gate, and it just says there's an error.
Yeah, I haven't looked for it.
Yeah.
It's on it. Yeah, I was trying to yeah, I just haven't.
It's pretty simple to find. I'm not endorsing that you find it that way, but if you just Google it, you'll find it.
So I got an error in
Yeah.
like when I put a C NOT gate, it gets an error.
Okay, sure. I'll come over and actually see, and then try and reproduce it for the video. The fun of being in person. Okay, so.
I think even if I just put a NOT gate, it's
Huh.
a different the output works, but
Yeah, the output works.
there's some error here. And
Yeah,
so
so
if
it
I
was
put a C
what, it
NOT
was
gate,
eight
it only
control
shows up
B,
as a
right?
9.
Oh, weird, wasn't it B?
And then
Oh, is it the old
that's
one?
clearly the problem. Like, yeah, you fix it,
Yeah.
it doesn't.
It doesn't like it either.
Oh, I see.
Huh.
So you flip the space for
I don't see anything different from my screen and all. If you try reloading the program, and, I don't know, man.
I'm not sure what the problem is. It just says multiple errors, and I don't even know how to read.
Oh my God.
Yeah, actually, I viewed it once. If you like hover over it.
You can see what the error code
It
is.
said it just said gate X, not the line.
Oh, that's spaceship key. Okay. Yeah, maybe if you haven't tried reloading, maybe try that. If you have a different browser, maybe try that.
Yeah.
I'm doing it on Firefox, but I don't know if that makes a difference or not. Hopefully
No
not.
problem, I can try.
Okay. Yeah.
Flip a, oh, okay.
Yeah. So again, I don't know how to do it on the graphical interface, but I just type it in the
Oh, okay.
text and then flip 1 to 0,
That
and
makes sense.
then the next one.
People
Next one.
control B. Okay.
So A
So the
controls
second one's
B,
the one you control.
and then what was the second part?
Oh, sorry, I'll put it up on the actual slide. So it was, where is
Still
it?
getting used to that.
So A controls B and C controls B.
Okay. It's launch composer.
Yes.
So that means that in both cases we flip B if A or C is true, right?
Yes, absolutely.
Yeah,
That's
the
the one.
notation's kind of wonky.
It is very strange. I agree.
Yeah.
It's very clunky and it's strange to get used to.
Yeah.
What is
So
the
it
X?
doesn't
Like,
apply
why is
for
it-
some
Oh,
reason.
really?
I think it's just to be supposed to control not. I think they say it's like CX is the controlled not gate.
Oh, I get it.
I'm not sure why they put X as not, but here we are. Yeah, yeah, it's weird notation. So I guess it'll be control X or Tolfi gate if it's the double control. And I'm not sure how they notate that, but I'm sure we'll see it at some point.
Okay, yeah, so for the record, it's Safari is more.
So Safari is bad. All right, so don't use Safari. Hopefully Chrome or Firefox should do the
Yeah,
trick.
Chrome is good.
Okay.
Yeah, Chrome works.
All right. Anyone having any troubles or anything like that? Or everyone proud about what they think the gate should be at? Or okay, okay, all right, yeah. So we'll do that. So yeah, the best approximation that I had. I'll go to the correct orientation circuit. Oh wait, no, that's not the one. No, that's not the one either. Well, we'll use this one and flip it because that's actually not what it's supposed to be. Let me get rid of these. So what I had written originally was that's the one, and then so that'll be two. What is it? 0 controls 1. So something a little bit like that, or it could be flipped around. I guess the order I don't think matters too much, but yeah. So yeah, hopefully everyone should have that, and that's like the basic of the gate. So now what I want you to do, having this gate, if you can follow the logic of it, so like taking the same approach, I mean, it's the exact same thing, but I want you to add another column in your truth table there, and then make it say, like, call it just like gate or something like that. And then convince yourself, or like go through and run it through like in the gate, that this circuit is actually equivalent on the truth table to the truth table that we just wrote. So basically just look at all the lines and say, okay, if A, B, and C are all positive on the line, what would the output be? And then do that. If you want to too, you could also physically in Composer go through and add the NOT gates to each of the lines to say the state, like this would be, well, since it's CAB, it's kind of reversed, but this should be B is set to 1. So this is 0, 1, no, that would be 0, 0, 1. But I find that a little bit more confusing. So if you can try and like mix it around and make it the way that you would do it, and then reproduce the last column based off of the circuit, if that makes sense. And again, any questions, please let me know.
So is there no difference between when they did in the text one, it says sum, and then it shows like the stick in the bracket, but it puts them all together, C, comma, A, and B.
This one right here, you mean?
That one, so how, you see how it breaks it up into C, and then A, and B?
Yes.
All the separate brackets?
Yes.
Versus the line above that, it puts C, A, and B
all together.
Does it matter?
So it kind of matters from a math standpoint, but in this case, we're gonna like say that like functionally it is kind of like equivalent for our case scenario. Yeah. So like I'm pretty sure you can't just like do it in there normally. Let me double check with Dr. Sabri though to make sure I'm not telling you complete nonsense though. I'll make a little question list. So yeah, can you just sum them together in there in the notation? Yeah, because basically, I know in Brockhet notation, there's very specific ways that you need to combine things together to actually like make it do the computation of putting those into the same thing. So Good question, though. Yeah, I'm also for every you guys that lecture, great questions you're asking, by the way. I was really like, those are some good ones that like I would definitely ask as well. Not saying I'm good or anything like that, but like, yeah, those are like, I really appreciate the like activeness and the questions and stuff like that. So, has everyone followed along, at least for the last column of the gate, or any questions or anything like that? Okay, yeah, we'll take this one up. I'll just give you I'll jump to the end and say that it is literally the exact same, as you kind of would have figured. What else would we be doing it for? So yeah, functionally, these gates are pretty much the exact same from like an actual like table standpoint. They'll produce the exact same logic. You could also, if you look at the textbook, because later on, see that there is a example circuit that they give right here at the end. And you notice it looks a little bit different from ours, where the 0 is what's controlled and the X is the not. So this is a little bit different than what they wrote out at the top here, where it's control C. And actually, let me just switch this to scroll so you can see both at the same time. You'll see that it's a little bit different than the actual definition they put up here. But if you were to actually work through the actual, what's it called, the table of that as well, like the logic table of it, you'll see that functionally it comes out different. Only instead of having B as our sum line, we are actually having C as our sum line. So it's a little bit of a different naming. So as an exercise left for like doing, we'll just work through for the end of this tutorial, I want you guys to go through and make this functional circuit and then do the truth table for this circuit and what it would be if the sum was on line C. If you want to, you could don't have to necessarily work through all of it, but just as an exercise that I won't like actually show, do that, and then that's part of what we'll hand in for the actual tutorial. So yeah, and then the last thing after that is we're going to do another very simple example just to show actually how you run circuits on the actual IBM Composer itself. So yeah, I'll write that down as a thing to do, but yeah, just also follow along. I'll send a picture of that if needed, if anyone needs to remember that, or just write it down, whatever's easiest. But let's move on to the simpler example where we actually run something. And I'll show you guys something that's kind of fun, but also kind of wacky about quantum mechanics. So let's just start with an even simpler line, one where we have one quantum line going up there. And all we're going to do basically is start adding start with the very simplest case, which is a NOT gate. So to actually run it on the quantum computers that IBM has, you have to add a line of measurement as well. So I forgot what the notation was. That was at C greg. And then, nope, that's not the one. I'm just going to start with a new one and then go from there. New file, because it starts the default. C greg C3. Okay. So we're going to do one quantum line and one normal traditional line. Basically, because what you need to do when you measure your quantum lines, you need to have like a classical line and a quantum line, so the classical line can actually physically measure that quantum line. So we can add a NOT gate here, just as a very simple example, and then we're going to add a measurement, which is this little dial with a Z, almost looks like a voltmeter here. And when you add that to the line, you'll see that it adds something from the quantum line to the classical line, and that's the equivalent of us taking a measurement, collapsing the superposition of what you not, so we can actually do a proper reading. The probabilities that you see down here is IBM Composer's best guess, as Dr. Sabri has said, of what the state actually should be, but it's not the actual quantum measurement of it. It's just an approximation of what it should be, giving classical bits. So if you guys could just reproduce this right here. And then we'll set up and actually run it. So I'm just going to give this a name, example NOT circuit. All right, so if everyone's good with that, so what we're going to do just to actually run it is go up to the top right and set up and run. And you can see, thankfully, IBM has given us all these nice little servers that we can use to actually run it. I leave all the defaults saying this as default, except for actually choosing the server which you get to run on, so you can choose the system or simulator. And easy trick that I go through is because you have to go into a queue, because everyone it's time shared, like old time sharing computers. I like to find the computer with the least online. I'm not sure if that's actually the best way to get it done the fastest, but that's the one I choose. So I go to the system and then choose the one with the least online. But yeah, And then I will, since we don't have a lot of qubits, you can select it with any number of qubits in there, and then hit run on that simulator, and we should be good to go. You can name your job if you want. I just name it untitled, but I just hit run, and then it'll be sent to the simulator and then put into queue. Where it actually the job goes in, and I know Dr. Sabri's shown this before, but in the middle column, this is the composer files, then there's the composer jobs, and then the docs and tutorials. So the middle is your composer jobs. And you can see that we have one that was just run today, and thankfully it went through the whole process and got completed. So now we can see that this was actually physically run on a quantum computer, and it shows like someone set up a NOT gate and it was run and measured, and of the 1024 we sent through, all of them are set to 1, so that's as we expected. So basically just did a NOT gate and then ran 1024 simulations of it and said, okay, yep, it did the thing we wanted to do. But you'll see, and it'll part of the fun is what I want you guys to do is add a bunch of NOT gates to that example, and then see the same result. And so you can imagine on like a classical computer, this is fairly straightforward. It's just us adding a bunch of NOT gates, and it should just go, all right, 0, 1, 0, 1, 0, 1. But I want you to see when you run that same measurement on one of these quantum computers. I put about 10, maybe more if you want to be just sure to see the phenomenon, but put about 10, maybe we'll bump it up to 15 just for fun. And then try running that again. Let's see who's got the least online. I'll do that same one and run the job. Jobs, that's completed.
Did you get one?
Yeah.
Little one. Was it supposed to be? And I put 10, so yeah, I think so. 22, so. So cool.
Everyone says 1, so yeah, I'm curious what they all say. So theirs is still 1. Huh, that's not exactly what is supposed to happen. Huh. Let's try adding an odd number and see what happens. I don't know, I forgot if I was 15 or 13. I've had this run before and it had it work. So maybe it also just depends on which computer you're actually running it on. Let's see here. Oh, huh. Yeah, it's also giving just the right result. Well, that's not fun. Let me try with Hadamard gates, actually, H gates. And see if I can get the actual result that we're wanting to. Let's do with an even. So Hadamard gates, these are a little bit different than NOT gates, but you need to make sure that it's an even amount if you're trying to replicate this at home. Let's try running this on the simulator. Ending.
I also keep getting the expected number.
You keep also getting, dang it, okay. I swear that I've had this happen before, so you might just need to take my word in case this comes out. Weird, okay. Well, that is sometimes I guess the actual examples don't always work out. Let's try adding double the amount and see if we can get it. Let's try this. Maybe one with a lot of qubits. Did you get one?
Yeah, I
Okay.
got that from my first one.
Oh, did
It's
you?
like a mix of 0 and 1.
Okay, so what's the like actual numbers for it says what the 0 and 1 is?
So 0 is that frequency, like
Yeah,
49?
that's the one.
Yeah,
And then 1 is 535.
535. Did you do that for the? We're using Hadamard gates or NOT gates? How many gate was it? An odd number or an even number? For Hadamard, it's creating superpositions. You need to make sure it's an even number of gates.
I might have used that number.
Yeah. What about yourself? What did
I
you get?
got 0 was 43, and then 1 was 981.
981. That's closer to something that I might expect as like what it's saying. So as you can see, it's not a whole lot, but the expected value that you probably should have seen was 1 in this case scenario. But we got 43 counts where it wasn't exactly on the actual amount that we want. So what's the ratio of that? So that would be 43 out of the sum of both of those is are not correct. So that is, so about 4% like error on, so let's make the actual percentage, about 4% error on like that one example. Now it doesn't happen all the time, but that's a big problem in quantum computing, is the actual, like, so what this comes from is the noisiness of the actual computer itself and the wires. Because this has to be run at super cooled conditions, any thermal noise or any fluctuation will be a problem. Now, normally for like single series of circuits, it's fine, but when you start adding and like the worrying about like adding more and more gates together and where this like process, the error compounds, you start to see problems like this. So you can imagine this, it's not exactly the same, but an example, say if a computer running at gigahertz speeds, like our normal classical computers, that's about 1 billion operations a second. If you were to have a 5% error in that, that's like 5 million errors out of your thing per second. So not exactly great. You see that it's like not exactly there, and there's some problems that we don't see in classical computing, but just as an illustrative example that there is noise in these circuits, so it makes it not the best if we want to do something that we need each of it. You can do error correction, and it's not exactly one-to-one, but like it's just the idea that like as the error compounds, there's going to be a lot of problems with quantum computing. So that's one of the biggest problems they're trying to solve, is the noise and stuff like that in the line. So you can see it even by just running something as simple as that. Yeah. So any questions of anything we've covered so far?
So there's always like a noise factor, like no matter what.
Unfortunately, yes. Yeah, it's just that like when you have something that the phenomenon are just so quiet in this and what we're trying to measure that inherently there's going to be like a little bit of noise. Now it's more pronounced depending on what you run, as you can see. But that's why, you know, if we can, we're always going to try and do the classical math to say like, okay, what's the expected value? And then when we run it through the circuit, we'll see like what the actual value is. So, yeah. It's unfortunate, but we're best we can. Yeah. So that is pretty much everything I have covered for the tutorial. There is a hand-in that you might see posted on Avenue. So basically, it's kind of just like an attendance mark, like did you work through and see this and follow along. So I think the 4 things I put on the Dropbox to include are, let's actually go read it. So I think I said I wanted the logic table of it. Where does it see where it shows the actual what you want it to do? Edit folder maybe? Hopefully you guys can actually have access to see this. Okay, yeah. So just submit basically the three things we did. Like the NOT gates, and if you can, don't worry if you can't get it to give it where it gives you like an error rate or something like that. But yeah, you know, the one where you just put a bunch of NOT gates or Hadamard gates together. Include that, and if you saw any error, if not, no worries. The truth table of that sum circuit from 113, yeah, page 113, this one right here, include the truth table, and then also a screenshot of the actual truth table, or like what it looks like in the composer view. And that's it for the first tutorial. It's just a simple like hand in, show you did it, show you here. I know you guys were here, but until I learn everyone's names and stuff like that to make sure that everyone made it. So yeah, that'll be due tomorrow at 11:59, 11:59 Eastern Standard Time, obviously. And then yeah, so that's it. The only other homework that I have for you guys besides that is for the next tutorial in class going forward, and for your assignment, and try and install the Jupyter notebooks, Jupyter Labs Qiskit notebook. So if you do a quick Google, that's not how you spell Jupyter, but qiskit.org has a very simple setup for setting up your environment. And you can do this and actually download the Jupyter notebooks, or there's an online version that you can. So I can send that link if it's easier, but I will also say a quick Google, so I'll send that link in the announcements, as well as taking up that good question. So, okay, alrighty. So yeah, quick and easy. Hope all the tutorials are this easy, but if you guys have any questions, please let me know. But if not, thank you all for coming. I appreciate coming in for such a short amount of time. So, awesome. Thanks, guys. I'll stop that recording.